Not room for you in the tent. You're welcome to take your lunch elsewhere except for the third floor where people are working. So please avoid no eating on the third floor. The other brief announcement before we get started is that there's been a request that for the videos that the authors come and stand up front, all of them. So when we start the videos, please, if you're an author, come and stand up front. And when your video is showing, please take a step forward so everyone can identify you. So this is in the interest of promoting interactions and so people can identify you for questions and conversation afterwards. So for the speakers, there will be a timer. If your talk is longer than 5 minutes, she'll give you a 5-minute warning and a 1-minute warning. And for the 5-minute talks, you'll get a 1-minute warning. So our first speaker is Professor Amos Winter.
Great. Okay. Is the mic on? No.
All right. Can you hear me? I can also project. All right, great. So I'm going to tell you about our work on designing high-performance, low-cost, passive energy storage and return prosthetic feet, as well as how they're leading into the design of high-performance, low-cost prosthetic knees. My name is Amos Winter. I'm a professor of mechanical engineering at MIT. And my research group, the Global Engineering Lab, focuses on designing technologies for developing in emerging markets. And in this case, what we're trying to do is make low-cost prosthetic limbs particularly for the tens of millions of people in the developing world. And the interesting research challenge behind this is we want to quantitatively predict the mechanical design and behavior of the limb in order for it to induce a desired biomechanical response. And so to give you a sense of why this is important, this is a knee user in India using a common knee and foot prosthesis, and you can see their gait is pretty far from what able-bodied gait would be. And people in this market want to look able-bodied to avoid stigmas associated with disability, and also they're often fit with limbs very quickly in a camp-type setting. So having a predictive model where you could say, okay, given a body size, body type, leg length, weight, and everything, here's the limb that should work well for you, would work pretty well in those situations. Now, our approach to this, as far as this quantification of the performance of the limb, we're trying to go right down to fundamental physics and think about these limbs kind of like springs. And so, if you have a linear spring and you apply a force to it and it deflects, you can relate that force and deflection with a stiffness, right? That's the constitutive relationship of the spring. We're trying to do the same thing with feet. And what we're particularly interested in is the behavior of the lower leg for two reasons. The first is the lower leg is the last segment of the person's natural body that's connected to the prosthesis. So that's what they feel, that's what they interact with. They don't actually feel what the foot is doing. And the second is this black box view of the problem enables us to not try to replicate an able-bodied foot necessarily, but maybe open up our design options a little further. So this lower leg trajectory framework that we use is based on first using a reference set of kinetic data. So ground reaction forces and a translation of the COP in the foot during a step. And then it also tracks the motion of the lower leg segment. So the X, Y coordinates at the knee and the angular motion of the leg. And so ideally, what we could do is connect these reference kinetics and kinematics through some sort of optimized function of the stiffness and the geometry of a foot. So what that looks like in action is here's a foot that we're going to optimize with the lower leg trajectory error. The first thing we do is choose those reference kinetics and kinematics. Then we also choose a foot architecture where we can prescribe the stiffness and the geometry of the foot. Then what we do is we apply the kinetics to the foot. We look at the deflection through the step and we track the motion of the foot through the step and compare that motion back to our reference with this lower leg trajectory error function, which is a root mean squared error function. And for x, y, and theta, we're looking at our predicted motion, our reference motion, and we're normalizing that by the mean of the motion. And we're also looking at this in each point in time during the step. And so to give you some physical intuition about how this works, ideally we'd have an LLT value of 0, which means we have a perfect replication of our kinetics and kinematics if we get our stiffness and geometry right. And if we have an LLT value greater than 0, we'd expect some sort of compensation as the person's walking. So we've now taken this theory and made feet, and this is our first proof of concept foot. And I don't know why my videos aren't starting, but here we go. You can see this foot in action. deflecting, and it uses a nylon U-shaped spring. We use nylon because it has a very high strain energy density and minimal hysteresis. And so if we look at the results of our first subject testing this foot, we used physiological reference data in the kinetics and kinematics to design this foot. And those data come from David Winter for a female patient of 55 kilograms. Our predicted LT value was around 0.2. The test subject we used was about the same size and weight of our reference. And these are data averaged over 5 steps. So if we first look at our kinetic data and look at the ground reaction force, so the dashed line is our reference, the solid line is our prosthetic side, and the gray line is our sound side. And qualitatively, we're getting about the right shape throughout the stance phase, and we're also getting qualitatively the right center of pressure progression. And if we look at that a little deeper and analyze it, and look at the root mean squared error through the step, normalized by the body weight of the person and their foot length, and comparing both sound and prosthetic side, we're getting about a kinetic accuracy of about 17%. And then if we look at kinetics, qualitatively they look, or kinematics rather, qualitatively they look pretty good throughout the step. And again, we can look at that in a little more detail. And here we're normalizing in the same method as we use for the LLTE framework. We're using the average values of X, Y, and theta to normalize. And again, we're getting about kinematic accuracy within 20%. And this is not perfect, certainly, but I think it's kind of an 80-20 type solution, that we're predicting this before anybody uses this foot, and they put it on, and they're walking actually pretty well with it. So what we've done now is use this framework to start designing single-part structures of compliant energy storage and return feet. And this is showing a wide Bezier curve, showing the shape of our foot, where all the red parameters here, we can plug into a genetic algorithm and optimize that shape of the foot for low lower leg trajectory error. And this is what the resulting foot looks like. And we have a bunch of these around here if you want to check them out and play with them this week. And this was a test subject last summer using one of our first feet. And we had 6 people in this first test in India. And particularly with the younger subjects, they really liked the energy storage and return, which is much better than the current feet used in this market. And with this framework, we're also able to investigate how the shape of the foot would change as we start changing parameters of the patient who would use it. So this is showing the same height person and limb length of the person as we change their body weight from 40 to 65 kilograms. And you can see that the foot shape changes rather drastically. But what's nice is we can predict that. And unfortunately, we had planned to test these new feet at Northwestern this spring. This is funded by the DoD and tested at a VA research center now, so we're about over 6 months in our IRB approval weight process, but we'll do it this summer, and we'll test 5 people of different body weights and body sizes to see, are they still getting the benefits we want. And then finally, another cool part of this project is we've teamed up now with Vibram, the hiking boot manufacturer, to make a cosmetic overmold of our foot, as well as a high wear, high traction sole. And so you can see our keel inside the foot here. And at amortized levels of production, including mold and all the material costs, we're projecting about a $15 cost of this product, which is pretty good for this market in an energy storage return foot. And again, these are going to be tested this summer in India with the target population, and we're making the molds for these right now. Yeah?
What does amortize mean in this sense?
It means we have to pay about $10,000 per mold, and so we'd produce on the order of 20,000 minimum feet a year, and so you build in paying off that mold cost with the cost of the foot over a certain amount of time. What's that?
But not the R&D.
Not the R&D, no, we're not because we're doing that. So what's cool about this now is we have a quantitative model we can start feeding into knee designs. So imagine we have a foot that we know how it behaves, we know its constitutive behavior, and we also have kinematic and kinetic data from a transtibial amputee that has used this foot. We can then take that data, we can adjust the GRF profiles based on the mass differences between a transtibial and a transfemoral amputee. So this is just showing, here's our GRF profile we guess for above knee amputee. We take our transtibial and we minus the force changes due to mass differences because of acceleration and gravity. And then we can plug that back using inverse dynamics to figure out joint torques throughout the body and joint torque at the knee. What comes out of this is a pretty interesting sensitivity of how knee torque would change as you start varying, in this case, thigh mass, and we get upwards of 100% change in the ideal torque profile to induce those kinematics that we want. But also what this does is it gives us a roadmap for how we could potentially replicate this target profile in black with a series of mechanisms that we're now showing in the purple line. So I'm going to tell you about how we're doing that right now, using a series of springs and dampers that are passively triggered to make this thing work correctly. So here's a view of our knee, and if we look first at the stance phase, our knee actually incorporates an early stance latch to prevent buckling if the patient stumbles. And what's unique about this latch is the virtual axis of the latch is actually down near the foot, and as the GRF progresses past that point, the latch will open. So what that looks like in action is here's the GRF vector. It's progressing forward, it's undoing the latch, and what's nice about this too is it makes a very distinct stable versus unlatched zone, so you know when it's going to trigger an unlatch. The second point we've incorporated in is an early stance flexion axis, which is another axis where we can get this behavior of knee flexion if we desire, so that's an option that we're going to keep playing around with. And then in the middle of the gait cycle, we have to damp the knee as we transition from stance to swing. So here's a viscous damper that we've had to design. And here's a video of a person actually using the damper and the latch integrated together. And we're seeing some nice gait behaviors here where they're inducing late stance knee flexion going into swing. And in our tests in India with patients thus far, they have preferred damping value around our optimal. If we go much bigger or much lower, they aren't preferring that. But we're going to follow up and do further testing in Northwestern this summer. And then the final element of this knee is that instead of damping in late swing, we actually use a spring to capture energy that can bump us up a little bit at the end of stance and give us this little bit of positive power that we need to get over that hump in the gait cycle. So in summary, what we're trying to build is the theory here where we can actually predict the constitutive behavior of feet and knees to get us the biomechanical performance we want. And this is particularly relevant in the developing world context we're working with, where you may have to use like a lookup table for a patient and prescribe them a knee or a foot within a matter of minutes. And then finally, this LTE framework I presented is agnostic. We use physiological reference kinematic and kinetic data, but we could use data from anything. You can minimize metabolic cost, stability, improve comfort, and we're actually looking into different gait activities, particularly for military applications like walking up and down slopes and on rough terrain. So you tell us. I was excited to see the new data set that somebody presented earlier this morning. So thanks very much. I'm happy to take a bunch of questions, and thanks to researchers, sponsors. There's more info.
Questions, so
Sure.
here. I
Yep.
have two questions.
Okay.
One is, you didn't quite say it, but in these loops, there's some energy involved, and so there's only so good that you could do according to, assuming there's no energy source. You're bounded by that. You didn't say how close you are to the sort of theoretical limit.
I have a backup slide just for that, Andy. So what this is showing is that vertical dash line right here corresponds to when like a physiological foot has the same amount of negative work it's done versus positive work, its output. And so this is the point when we'd think a passive foot would kind of run out of energy, and this is where we'd expect to see more deviation. And I think, we're kind of seeing that here, and we're seeing some more deviation in the end of the kinematics too. So we are looking at that.
But there's you could just have a theoretical, like, of all passive curves, there's a best curve in terms that matches energy conservation.
Yeah, so I'll repeat Andy's question. Without the feedback, Max? Okay. So what Andy was alluding to is maybe we could have a kinetic and kinematic data set that corresponds to a passive foot, where we're not doing any positive work. And absolutely, if we knew that ideal data set for a passive foot, we could plug it in and optimize the structure and the stiffness of the foot to do that. Conversely, we can also do this for a powered foot. So if you can do positive work, we can help you design the torque profile of the output to do that.
Can I do a second one? Which is a constitutive law. You have force position, force velocity relations for one trajectory, but the constitutive law is supposed to work for all trajectories. So the question is, how far off do people get when they're not just in a steady gait, but they're correcting and things like that?
And we don't know yet. This is kind of the first order model of trying to relate predictions to experimental results. But absolutely, Andy, we want to do different walking profiles as well as potentially more degrees of freedom. But I think the LLT framework can accommodate that.
Hi, right here. So there's some evidence now that there's active modulation of foot stiffness within stance and between various types of gaits. Have you looked at like actively modulating the stiffness of your feet? Or I mean, I know that all of that what you showed was dead springs in some sense, but what's your take on?
I would love to if you can do it for less than $20. That's the issue.
We should talk.
Yeah, absolutely. Elliot works on this stuff, and it's awesome work. I think, and I think we were talking last night, in even a prescription setting, you could have a person walk with the foot, you can dial it in. I hope I'm not giving away some toys for you, Elliot. But that's a great setting. We're working in a very different setting. There's often limb camps where people get cycled through in the matter of minutes to hours.
Right.
So if we can do some prediction and get them a good foot, that has value.
Yeah.
So we have one quick question in the back and then one online question, and then we're probably moving on to the next topic. So in the back.
So can you speak, so with this population, with amputees, I almost bet that their socket fit is not all that great in comparison to those in the States, right? So can you speak to like how you can either use different metrics to compensate for this, or have you looked at different socket fits with relation to this population? Because that's going to be a huge issue with how they're going to react.
Yeah, you're absolutely right. The question was, are we taking into account socket fit? We are currently modeling this as a rigid connection between the prosthesis and the socket. In reality, that is not true. In at least the clinical tests we've done at Northwestern, it has been rigid enough that it seems like our predictions are pretty good. I don't think you'll ever totally take the human out of the loop in the prescription process, because even the organization we work with, they'll shave down the socket, they'll try to find the pressure points to make it comfortable. But thus far, we haven't seen that we have to add another compliance into the leg to account for the socket. This is working well enough.
We have time. Check.
We have a Slack question.
Yeah, I'll choose that. Yeah. We have.
I can read it too.
Hello, there we go. We have time for one Slack question, and it is, have you tested any currently available prosthetic ankles with your metric and framework?
We are doing that starting this summer with our collaborator Matthew Major at Northwestern. So we want to get a sense of like how good is their good compared to how good is our good, and we could calculate an LTE value for a commercial foot. We haven't done that yet, but we'd like to, where we measure the stiffness, the force deflection response of the foot throughout stance phase, and then can actually calculate how good should it be. So it's part of our future work, certainly. Manoj? The damping ratio? We intentionally try, for the knee? Oh, okay. The knee is optimized with a genetic algorithm where we can change the damping ratio in order to match that ideal target curve versus what we expect our knee will do as it moves through the same kinematic profile. So maybe I didn't say that explicitly enough, but when we simulate the knee, we assume it's moving with the same kinematics as our target. And so if we put in different damping ratios, we'll get different torque profiles.
And why GA? Why not other optimization methods, PSO, ICA?
We could use others. We just started with the GA.
Oh, thank you.
Yeah. It doesn't preclude us from trying others.
Yeah.
Manoj, you want to sneak in one final question?
I don't know, maybe I want to very, very slightly object to Andy's question.
Okay.
He said something like, if you had power at the ankle, you could do better, which is presumably true.
Yeah.
But it feels like even if you had power at the ankle, the energetics of the system is still different. You have this free source of power. So even if the system can approach the kinematic and kinetic target, it may not want to. It may not be the right thing for it to do because it has this free source of power. It wants to use it, so it might well walk asymmetrically.
Could walk
because
asymmetrically.
there's this free source of power.
And then also you have to account for additional weight. So that distal weight, we've done the sensitivities on this. That distal weight, particularly for a knee user, makes a big impact on the hip energy. So if you go from like 20 to 100% leg mass, you change your hip energetics by like 20% mechanical energy.
Right. And if you want to really fool the system, you have to tap into sensors like Max does, perhaps, like the sensors that deal with energetics, maybe.
Sure. But again, we're trying to do this so dirt cheap and do as best as we can.
Okay, let's thank our speaker.